Today, I have come up with you to explain a very surprising theory that is quantum entanglement. This theory has negated the observations of Einstein in respect of interconnectedness of particles regardless of the distance, which was termed as spooky action at a distance by Albert Einstein. Quantum entanglement refers to a phenomenon in which the properties of two or more particles connected in such a way that the state of one particle cannot be described independently of the state of the other. As a result, any change made to one particle instantaneously affects the other state of the other particle, regardless of the distance separating them. Quantum entanglement is indeed like particles sharing a secret connection that allows them to communicate instantly, no matter how far apart they are. It's as if they are best friends who can sense each other's actions instantaneously, even if they are on opposite sides of the universe. In simple terms, entanglement is a special thing that happens in quantum world, which is the super tiny world of subatomic particles like electrons and photons. In classical physics, objects can be separated and do their own thing. But in the quantum world, particles can become connected in a way that's like magic. This connection is called entanglement. It means that even if these particles are far apart, what happens to one instantly affects the other. It's like they are linked together in a way that's completely different from what we are used to in classical physics. This odd connection between the two particles is instantaneous, seemingly breaking the fundamental law of the universe. This weird connection puzzled Einstein so much that he called it as the spooky action at a distance and dismissed the idea of entanglement. It's like these particles have a secret bond that lets them talk to each other super fast, breaking all the normal rules of communication. In 1935, physicist Erwin Schrödinger introduced the term entanglement, highlighting its significance as a fundamental aspect of quantum mechanics. Until 1970s, scientists were still debating whether quantum entanglement was real. It was a big deal because even Einstein wasn't sure about it. But with the invention of new experimental tools and courageous researchers, they finally proved that entanglement is indeed a genuine phenomenon. The 2022 Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for their groundbreaking discoveries related to quantum entanglement. In short, what they have discovered is that entangled particles behave like a single unit, even if they are separated far, far away. In quantum world, objects behaving according to the principles of quantum mechanics, which are fundamentally different from classical mechanics. In quantum mechanics, particles can exist in multiple states simultaneously. They can be in two places at once, and they can be interconnected through a phenomena like entanglement. Quantum mechanics also introduces concepts such as wave-particle duality and uncertainty principle, which have no analogues in classical physics. In the classical world, things act predictably, like when you throw a ball, it goes where you expect. But in the tiny quantum world of atoms and particles, things get weird. Particles can be in multiple places at the same time, and they can influence each other's instantly, even if they are far away. It's like they are playing a completely different set of rules that doesn't match up with our daily life experiences. In classical physics, there's no direct analog to the concept of entangled particles as it is understood in quantum mechanics. In classical physics, objects are typically described by classical mechanics, which assumes that they are well-defined properties such as position, velocity, and momentum. The behavior of classical objects is deterministic, meaning that if you know the initial conditions of a system and the laws governing its behavior, such as Newton's laws of motion, you can predict its future state with certainty. The theory of quantum entanglement can be understood by the following example. Let's imagine you have two magical coins. These coins are special because when you look at one, you automatically know what the other one looks like, no matter how far it is. So, if one coin shows a picture of a cat, the other coin will also show a picture of the cat, even if it's on the other side of the universe or another side of the room. Now, these coins are like tiny particles in the world of really, really small things called atoms. When atoms are tangled up like this, we call it quantum entanglement. It's like they are best friends who always know what the other one is doing, no matter how far apart they are. Entanglement is a distinctly quantum phenomenon that arises due to the principle of quantum superposition, measurement, and non-locality. The strange part of quantum entanglement is that when you measure something about one particle in an entangled pair, you immediately know what the other one is like, even if they are millions of light years apart. However, in quantum mechanics, various types of particles can become entangled with each other. Here are some common examples: photons, electrons, ions, atoms, superconducting qubits, and nuclei. These are just a few examples of particles that can become entangled in quantum systems. The choice of particles often depends on the specific experimental setup and the properties being studied. Entanglement can occur between particles of the same type or between different types of particles, depending on the desired outcome of the experiment. Two particles can be interconnected or intertwined in several ways in quantum mechanics, like spin entanglement, polarization entanglement, position momentum entanglement, energy entanglement, composite entanglement, etc. The nature of entanglement can vary depending on different properties of particles involved in the interactions between them. It could be important to mention here that when two or more particles become entangled, their behavior exhibits correlations that are not observed in classical systems. The specific behavior of entangled objects can vary depending on type of entanglement involved. For example, particles may be entangled based on their spin, polarization, position, momentum, or other properties, each of which can be led to different experimental outcomes. Entangled objects can exist in superposition of states, where they simultaneously possess multiple possible properties until they are measured. In summary, while the behavior of entangled objects is fundamentally different from classical systems, the exact nature of the behavior depends on various factors, such as type of entanglement, the properties being measured, and the experimental conditions. Quantum entanglement lies at the heart of many fascinating phenomena in quantum mechanics and has profound implications for our understanding and nature of reality at the microscopic level. This phenomenon is one of the fundamental aspects of quantum mechanics and forms the basis for technologies like quantum computing and quantum cryptography. It's important to note that this isn't due to the particles communicating at speeds faster than light, but rather because of their states were determined at the time of their entanglement. When particles are entangled, their states are described by a single joint wave function rather than individual wave function. This entangled state is often described as being non-local, meaning that measurements made on one particle can instantaneously affect the state of the other, no matter how far apart they are. Thus, it is very clear from the above discussions that quantum entanglement is a phenomenon that occurs when two particles like photons or electrons become connected. This connection persists when the particles are separated by vast distances. Conclusively, quantum entanglement is a key resource in quantum information processing and quantum computing, as it enables certain tasks such as quantum teleportation, quantum cryptography, and superdense coding. Thank you.